Hello students, welcome back. We completed section 1, the arithmetic property. Now let's go to section 2 and discuss the order property, the property of real numbers associated to inequalities. The set of real numbers is linearly ordered or totally ordered. They mean the same thing. So linearly ordered or totally ordered. As a result, each real number can be placed on a line. So what do you mean by linearly ordered or totally ordered? First, a trichotomy. Given pair of real numbers x and y, one and only one of these three will hold. X is less than y is less than x, or x and y are the same. One and only one of them will hold. So these or are actually not exactly or, but exclusively or simply XOR. So one and only one of these three will hold, so we call it trichotomy. But throw the last one away and look at the first two, then you can see that x is less than y and y is less than x cannot happen at the same time, so it covers asymmetry. And also comparability, any pair of real numbers can be compared. One is less than the other, or vice versa, or equal. And then, of course, trichotomy. Put together these two properties, we get the linear order and the linearly ordered set. Another way to accomplish the same thing is to use the semi-inequalities. And I don't like it very much because we have to check 4 properties if we go with less than or equal. If I use strict inequality, I have to check only these two. So it's simpler this way. But there are some advantages to do it with the ladder method here, which I just highlighted in blue. Because first 3 properties, what are those? These are the properties for partially ordered set. And then we have the last one, the linearity or the comparability. That is, every pair of real numbers can be compared with less than or equal. Yeah, we can do it like this too, but I prefer to do it the other way using strict inequality because it's simpler. And then we have 2 more important properties. Now this time, these 2 properties put together the ordering and arithmetic operation together. First, when x is less than or equal to y, x plus z is less than or equal to y plus z. So the inequality preserves the addition. If I add the same number to both left-hand side and right-hand side, the inequality is preserved. Next, it preserves the positive multiplication. X is less than y and z is greater than 0, then x times z is less than or equal to y times z. Now, what if I multiply negative number? Well, everybody knows what it is. We have to flip for the direction of the inequality, but this is not one of the basic properties. We can actually prove it. The proof is not difficult. All you have to do is flip it over. Yeah, you can prove it from the other properties. Well, let's see. Shall we go ahead and prove it? Okay, all right. So basically, we have to, fill in the middle. So how do we do that? X times z is less than or equal to y times z. Let's put dot in there. Okay, all right. And then subtract this one away and subtract that one away. Then, oh well, this can wait. Okay, and then on second thought, let's do this without this dot. Too many dots, too many typings. Okay, all right. And then you can easily see that but then again, what is this negative xz, or the additive inverse of x times z? Is the same as this. Okay, now if you do the same thing to push this one to the other side, then we are going to get the desired result, right? So negative yz plus yz plus x negative z. Okay, all right. And then these two will be 0. So negative yz is less than or equal to x times negative z, but we do the same thing. What is negative yz? The additive inverse of y times z, that's equal to y times negative z. Remember doing this? We did it here in this problem. Remember this? Yeah, these. Okay, the details are left to the students. What I'm trying to say is flipping the direction of the inequality when multiplying by negative numbers, that's something you can prove from the basic properties. So this one down here is not one of those essential properties. These four are essential. The trichotomy and transitivity put together, we get linearly ordered set. And then let's put together the linear order and arithmetics together using these two. The linear order and addition, and the linear order and the multiplication. Positive multiplication, to be a little bit more precise. Alright, so much for the order properties of R. We have some interesting examples. Okay, if you multiply by a negative number, then you have to flip the direction of the inequality, and we just did it. Okay, how about the next one? X is greater than 0, then negative x is less than 0. X is less than 0, then negative x is greater than 0. And that too, you can just subtract away. So add negative x to both left hand side and right hand side, and that's going to be it. How about this one? X is less than 0 and y is less than 0. X times y is greater than 0. Well, okay, it's going to be an application from this one here. So y is less than 0. Multiply x to both left hand side and right hand side. Right hand side, x times 0, we get 0. And then we have to flip the direction of the inequality. The details are left to the students. Here's something interesting. Can we actually prove 0 is less than 1? And 0 is not equal to 1. That much is certain, because that's the way we built this arithmetic properties of real numbers. Let's see. Here we go. Yeah. The unity is non-zero. You see this Rx symbol? All real numbers other than 0. So non-zero real number 1 exists. So unity cannot be equal to the identity. So that much is certain. We know that 0 and 1 are not equal. But we have to go one step further and prove that 1 is greater than 0. Well, how can we do that? Well, let me give you a hint. Try to consider this, try to prove this one. No matter what x is, oh wait, excuse me, when x equals to 0, then it doesn't work. So, all right, x is non-zero, then x squared is greater than 0. Okay, all right, you can prove this one. When x is greater than 0, x times x is greater than 0, because positive times positive. Now when x is less than 0, x squared is still greater than 0, because this is negative times negative. And then as a special case, you can prove 1 is greater than 0. 1 is 1 squared. Well, details are left to the students. And of course, that's not the only way to prove it. There are different ways to prove it. In any case, make sure that your proof goes all the way back to the basic properties, those field properties that we discussed in section 1, and then these 4 properties: linear ordering, and preserves addition, preserves positive multiplication, those 4 properties. Okay, what else? Dense distribution. Okay, all right. Real numbers are densely distributed, and rational numbers are also densely distributed. Between any pair of distinct real numbers, there exists at least one real number in between. Consequently, there are infinitely many. You know, between any two, oh, never mind. Simply enough, so I'll leave the details to you. Let's see. Do we have something similar for rational numbers? Yes. Do you have something similar for integers? No. See the difference? How about part B? Between any pair of distinct rational numbers, there exists at least one rational number. Consequently, there are infinitely many. Part C, the smallest positive real number doesn't exist. Well, any positive real number and 0, well, we have a pair of real numbers, so there got to be something in between, right? Okay, all right, that's where I'm going to stop, and I want you to work through these. Got it? Did everybody get it? Well, without loss of generality, we can assume one is greater than the other. Otherwise, we can just rename it. If x is greater, then rename x and y so that y is greater. And then we can find appropriate c by selecting the midpoint, the average, x plus y over 2. It's that easy. Of course, if you don't want to select midpoint, you can select something else as well, something like this, if you will, but I don't really understand why would anybody write something like this in favor of something simpler. Well, I just wanted to make a point that there are infinitely many. And you can do exactly the same thing to rational numbers. Yeah, that's a rational number too, right? How about irrational numbers? Between any pair of irrational numbers, can you always find at least one irrational number in between? Think about that. It's not that easy. And as for this one, yeah, okay. Any positive real number and 0, you can find something in between. So that cannot be the minimum. And this dense distribution property leads to boom, 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 the epsilon principle, which is going to be extremely important in real analysis. I'm not going to go there too deeply. You can set up and prove those, and those are going to be good exercises, but that's where I'm going to stop. I'm not going to go too deeply into epsilon principle. It'll become really hard too quickly.